Welcome to the Deep Dive. Today we're plunging into a new research paper that's causing quite a stir in the world of training large language models.
That's right. We're looking at excerpts from Mask-Enhanced Autoregressive Prediction. Pay less attention to learn more by Zhuang and colleagues PMLR 2025, plus some notes you've shared.
Exactly, and our mission for this deep dive is to really unpack this new training idea they call MEAP, Mask-Enhanced Autoregressive Prediction.
Yeah, we want to dig into the academic details. What's the core innovation? How does it actually work? And crucially, how does it aim to fix that problem LLMs have with finding info in really long texts?
Okay, so let's set the stage. Before MEAP came along, what was the standard playbook for training these big models?
Well, you really had two main players, right? Each with its own sort of pros and cons.
Okay.
The first one, and the one powering most of the big generative models we see now, is next token prediction, NTP.
Ah, yes, the standard, right? Just predict the very next word.
Exactly that. It's the foundation for models like, GPT, Llama 3, Gemini 1.5 Pro, DeepSeek-V3, basically all the big decoder-only transformers.
And it's great for generation, making text flow smoothly.
Fantastic for it because it learns to build sequences naturally, token by token. But, and here's the catch, the really interesting bit. NTP models, while they're amazing generators, they have this well-known struggle. They're not always great at pulling out specific facts or details, especially when the context gets super long.
Right. You feed it a huge document, ask a precise question, and it might just whiff or make something up.
Precisely. Good for stories, maybe less reliable as a high-precision search engine over lots of text.
Okay, so that's NTP. What was the other main approach?
That would be masked language modeling, or MLM. Think BERT.
Ah, the fill-in-the-blanks approach.
Exactly. You hide some words, the model predicts what was hidden. It's a denoising kind of task. And this makes MLM really good at understanding sentence structure, context from both sides, bidirectional understanding, great for information retrieval, classification tasks.
But MLM isn't really designed for generating long, creative text like NTP, is it?
Generally, no, and often MLM setups used encoder-decoder architectures, or at least needed that bidirectional view, which can add complexity compared to the simpler decoder-only setup that works so well for scaling up NTP.
Okay, so I see the dilemma. You've got NTP, good generator, scalable architecture, but weak on long context retrieval. Then MLM, good retriever, but not a natural generator, and maybe more complex architecture-wise.
That's the core tension, getting the best of both strong generation and strong retrieval within one efficient, scalable model. That's been the tricky part. People tried combining them, sure, but often ended up with complex, multi-stage training pipelines.
Right, not ideal. Which brings us to MEAP. This is the core innovation from Zhuang et al. Yeah. How do they try and fix this?
Okay, so the core idea is actually surprisingly simple conceptually, but the implications are pretty significant. They basically found a way to get the benefit of MLM learning from noisy or incomplete input, but within the standard NTP framework.
Without changing the whole architecture. Still decoder only.
Exactly, that's key. The mechanism is this. During training, they just randomly mask out a small fraction of the input tokens, say around 15% during pre-training. That seemed to be the sweet spot.
Okay, mask 15%, then what?
Then you just run the standard next token prediction objective on this mask input. The model still predicts the next token based on the previous ones using causal attention like normal.
So wait, it's still just predicting the next word left to right, but it's doing it on a sequence that has some holes punched in it.
That's it. You're feeding the normal NTP process slightly degraded input. And what's really neat is this adds basically zero extra computational cost during pre-training or inference compared to standard NTP. No new layers, no complex loss functions, just changing the data slightly.
Huh. So the idea is to force the model to be a bit more robust, maybe infer things better like MLM, but keeping the efficient NTP structure.
That's the intuition, drawing on that denoising idea from MLM, but keeping it autoregressive and efficient.
Okay, let's get into the nuts and bolts a bit more. Academically, how does this masking work in practice? Pre-training first.
Right. So pre-training, take your text sequence, randomly pick, say, 15% of the tokens, replace them with a special mask token, then train the model using the standard cross-entropy loss, predict the actual next token given the sequence so far, including any masks.
And it only looks backwards, causally.
Still causal attention, yes. When predicting token I, it sees tokens 1 to I1, whether they're masked or not. That 15% seems like a good balance, enough missing info to force learning, but not so much it totally breaks the language flow the Madi needs to learn.
Got it. Predict the next word, but sometimes the history has gaps. What about fine-tuning? You mentioned it's different there, especially for tasks like QA.
Yeah, it's a bit more tailored there, because in fine-tuning, you really don't want to accidentally mask the crucial piece of information the model needs for the task, like the answer itself.
Makes sense. So what do they do?
For supervised fine-tuning, particularly tasks like question answering, they actually duplicate the training example. So you feed the model the original sequence question, full context answer, and then you append a copy of that same sequence, but in the copy, you apply random masking, maybe a bit less, like 10%.
Okay, hold on. So the input is original Q plus context plus A, followed by masked Q plus context plus A. That's double the length.
It is double the length for that step, yes. But here's the clever bit about the loss calculation. The model processes this whole double sequence, but the training loss is only calculated on predicting the original unmasked tokens for the positions that were masked specifically within the answer span of the second copied sequence.
Whoa. Okay, so you're not just randomly trying to fill blanks everywhere. You're saying, look, here's the full clean context and answer points to first copy. Now, using that, I want you to focus on reconstructing the answer even when parts of it are hidden in this version points to second masked copy.
Precisely. It focuses the denoising effort right onto the critical output part while ensuring the model still has the full unmasked context available in the first part to learn from. It trains the model to retrieve and reconstruct the key info even if it's partially obscured, really leveraging the context. Especially useful if the answer itself is quite long.
That is clever. Okay, this brings up the big why, right? Why does this work? Why does making the model pay less attention by masking lead to learning more, especially for retrieval? What's the hypothesis?
Right. This is central to their argument. The authors hypothesize that MEAP works primarily because it encourages the model to learn more distinguishable attention scores.
More distinguishable attention. Okay, what does that mean in practice?
So, you know how transformers use attention, assigning weights to different input tokens to decide how much influence they should have?
Yeah.
Well, in very long sequences, standard NTP models can sometimes struggle. The attention might get spread too thin, like a thin layer of butter over too much bread, or sometimes it focuses too much on weird things, like the very first token, these attention sinks. It becomes hard for the model to really pinpoint the most important tokens.
Right, everything gets a similarly low score, maybe. Like a blurry picture where nothing stands out?
Kind of like that, yeah. A flat attention landscape. The hypothesis with MEAP is that by forcing the model to ignore the masked tokens during training because, well, they're masked, it implicitly learns to assign much less attention weight to those positions.
Okay, less attention on the mask spots.
And that has a knock-on effect. If you lower the attention on some tokens, the relative attention on the unmasked tokens becomes more pronounced. The differences between them get amplified. The model has to focus more intently on the information that's actually available.
So ignoring the noise makes the signal clearer. By reducing attention on masked tokens, the important unmasked ones pop out more.
That's the intuition, and they ran analogies to back this up. They found that in MEAP models, the masked tokens got, on average, 53.34% less attention than they would have in an NTP model. But crucially, this led to a 7.80% increase in attention variance specifically among the non-masked tokens.
Increase in attention variance. That means the attention scores on the useful tokens were more spread out, less uniform.
Exactly. Higher variance means more peaks and valleys in the attention landscape rather than a flat plane. The model gets better at differentiating signal from noise, assigning significantly higher scores to truly relevant tokens.
And this learned behavior, this more peaky attention, carries over to inference time, even when there are no masks.
That's what the evidence suggests. During inference on actual tasks, MEAP models focused much more strongly on the right stuff. They measured attention on answer-relevant tokens. MEAP put 34.5% of its attention there, compared to only 9.4% for NTP.
Wow, that's a huge shift.
It is. And conversely, attention on less relevant parts, like the context before the answer, dropped dramatically from 73.1% in NTP down to 49.1% in MEAP.
So it really learns to zoom in.
Precisely. The academic take is that MEAP learns more distinguishable attention scores by concentrating on a reduced set of non-masked tokens. This improves focus, reduces the influence of distracting context. It literally learns more by attending to fewer tokens during the training phase, and that pays dividends when it needs to find information later.
Okay, hypothesis is compelling. The mechanism seems smart. What about the results? Did it actually work in practice? What did the experiment show?
Ah, the proof is in the pudding, right? They ran a whole battery of tests, really focusing on those tricky long context tasks.
Like the needle in a haystack benchmark everyone talks about.
Exactly that one. Finding a specific sentence hidden in a massive text. Here, MEAP showed really significant gains over NTP, especially in data efficiency. Get this. For the 32,000 token context test, MEAP hit 85.8% accuracy after being trained on just 60 billion tokens.
Okay. And NTP?
Standard NTP needed roughly 200 billion tokens, more than 3 times the data, to get to a similar level of accuracy on that specific task.
Wow. That's not a small difference. That's potentially huge for training costs and time.
It really suggests MEAP picks up that long context retrieval skill much, much faster. And they have visuals, figure 3 in the paper, showing MEAP holding strong accuracy across different context lengths and where the needle is hidden, while NTP performance really degrades, especially past 24K tokens or so.
Okay, impressive on needle. What about more complex stuff, like finding answers across multiple documents, maybe with distractors thrown in?
That's the multi-document question answering task, MDQA. Tests exactly that robustness to distractors, finding info across long, potentially messy inputs. And again, MEAP consistently came out ahead. They saw gains of up to 30.6% in some pre-training setups and averaged about 11.77% improvement across different fine-tuning configurations. It seems much better at cutting through the noise.
And reasoning. Does better retrieval help with actually reasoning over long texts?
Seems like it. They used a multinodal reasoning task where the model has to find multiple pieces of information scattered across the text and integrate them. MEAP showed a consistent 6.6 percentage point average gain over NTP there. Better focus likely helps piece things together.
And you mentioned hallucination earlier.
Right, a nice side benefit. Because MEAP is better at finding the actual ground truth in the provided text, it tended to hallucinate less. They featured this in text summarization tasks and found consistently lower rates of contextual hallucination for MEAP compared to NTP. It stays more faithful to the source.
Okay, and was this just for one specific model type or size? Or did it work more generally?
That's important, yeah. They tested it across different architectures, Llama style, Mistral, Quen, and various model sizes. The benefits seem to hold up, suggesting MEAP isn't just a fluke for one setup, but potentially a more broadly applicable training paradigm.
We touched on efficiency. Let's nail that down. Pre-training and inference, you said no extra cost.
Correct. For pre-training and inference, computationally, it's the same cost as standard NTP. The masking happens to the data before it goes into the standard transformer blocks. Same architecture, same runtime.
But fine-tuning involves that duplication, doubling the sequence length per step. That must cost more per step, right?
Per step, yes, it does require more computation because the sequence is longer. You're processing twice the tokens. However,
There's a however.
there is. The paper shows that MEAP reaches better performance with significantly fewer training epochs or steps overall. They have a chart, figure 5, showing MEAP fine-tuned for just one epoch on MDQA, outperforming NTP trained for 2 full epochs.
So even though each fine-tuning step is heavier, it learns so much more effectively per step that you need way fewer steps to get superior results. The overall training cost to reach a target performance is actually lower.
That seems to be the case, exactly. The data utilization efficiency during fine-tuning is much higher. It learns those specific long context skills faster, offsetting the per-step cost when you look at the total training budget needed.
Okay, so let's wrap this up. What's the big picture here? MEAP seems like a surprisingly simple tweak on the surface, just mask some input.
It does seem simple, yeah, but it's an academically elegant way to tackle a really significant weakness in standard NTP models that struggle with accurate information retrieval from long contexts.
By sort of borrowing that denoising principle from MLM, but cleverly integrating it into the efficient decoder-only NTP setup we already use.
Exactly. It subtly forces the model to refine its attention mechanism, to learn to focus more sharply on relevant signals without changing the core architecture or adding costs during pre-training and inference.
And the results seem pretty compelling. Big gains in retrieval, better reasoning, less hallucination, better data efficiency, and it seems broadly applicable. It's a neat fusion of ideas.
It really makes a strong argument that sometimes small, principled changes to the training process or the data presentation can unlock significant capabilities, especially for challenges like long context understanding, where just scaling up hasn't been a complete solution.
Which definitely leaves us with something to think about. If this simple idea of paying less attention to learn more through masking works so well for long context retrieval, What other, maybe even counterintuitive tweaks to our standard training methods might be out there? What other simple changes could unlock new LLM abilities?
Right. And how might findings like this change how we think about building future models? Maybe it's not just about ever longer context windows, but about building smarter, more efficient ways for models to actually process and attend to the information within those windows. Food for thought.